The next stop on the machine translation nostalgia train is phrase-based models. The IBM models made the assumption that while a word could have many translations, the translation model itself couldn't really use the context that it needed to decide how to translate the word. And while the language model could carry some of this burden, one of the lessons of natural language processing is that you need context to truly understand how language is used. Let's take, for example, the German verb anstellen. There are a couple of things that make this word tricky to translate. First, it has a lot of different meanings. Stell dich nicht so an means don't make a fuss, but stell die Klimaanlage an means turn on the AC. It can also mean to hire somebody. It can be to faff about. And stell die Leiter an die Mauer an means to put the ladder against the wall. Oh, and that an? That's not part of anstellen. That's a preposition that means against. Second, you might have noticed that anstellen doesn't hold together very well. If you use it in some sentences, the an moves around in the sentence and goes to the end. And as we saw, the an itself can be a preposition, adding to the confusion. Now, my goal is not for this to be a German lesson, but the takeaway should be that you can have very different translations of the word anstellen. And if you're trying to translate anstellen into English, then you need to know the context to get this right. There are lots of different options. So let's see how this works in the model that held sway for about a decade in between the IBM models and the emergence of neural machine translation models. And the solution was to basically memorize as much of the sentence as you could through things called phrases, or a phrase memory. So you break up a source sentence into phrases and then translate each of those phrases. But while unlike the word-based models, you can use more of the context to make a translation. And then you've essentially outsourced the job of reordering the output translations to the language model once you have the component pieces from the phrase translations. So what we need to make this happen are potential translations for a phrase. For example, the German word natürlich can have any of these translations. So what are these phrases that we've been talking about? These phrases are just words that appear together on the source side and also appear together on the target side in some parallel text. Here, for example, are the translations of den Vorschlag. Sometimes it has punctuation, sometimes it doesn't, sometimes it's part of a possessive phrase, sometimes it gets turned into a pronoun in the translation. And I should emphasize that the phrase here doesn't mean it's a noun phrase, verb phrase, things like that, that you get out of probabilistic context-free grammars. Link in the description if you don't know what that is. So why not make it align with the grammar that we spent so much time learning about? Well, you could. And there was a whole line of research using synchronous context-free grammars that tried to do that by generating phrase trees and then source and target language simultaneously. But it ended up not being as flexible as these phrase-based translations. For example, the prior noun often helps you figure out what preposition you should use. You put the milk in the refrigerator, the magnet on the refrigerator, the mat in front of the refrigerator. That's not part of the prepositional phrase. So where do these phrases actually come from? They come from the alignments that we talked about in the IBM Model 1 discussion. To make a one-to-many alignment, plot the binary alignments as a grid, and then draw a square that includes all of the alignment from all of the words the alignment touches. So this middle phrase isn't okay because there's a German word aligned to an English word that isn't in the phrase. And you can write the same thing mathematically. The transitive closure of the alignments needs to be entirely in the phrase. Now, this results in some small phrases. Michael can align with Michael, but because assumes is aligned to everything in geht davon aus, then if you translate assumes, you must get everything in the alignment with it. But you don't have to stop there. You can get much longer phrases. Unless you have a cap on the size of your phrase table, you could get the whole darn sentence if you wanted to. The trick is to strike the right balance so that you can generalize. So you gather up a bunch of these phrases, then you need to score them. Basically count how often you produce the English phrases based on the total number of times you see the foreign side of the phrase. Then you can score the overall translations that get produced. You have a set of phrases that you translated. Each of those contributes something to the score based on the MLE estimate of the phrase translation probability, and then we add to that score how much we've moved around the phrases. Phrases that are close together in the source should normally be close together in the target. This, of course, holds true for some language pairs more than others. And if you were actually implementing these sorts of models, we'd talk more about what objective function you should use and how to combine reordering models, phrase translations, and the all-important language model score together. But given that these models are no longer state-of-the-art, what we're going to do next is instead talk about how these models influenced modern neural models. And in my mind, the biggest historical through line of these models is how to generate a translation given the source. How to decode your translation. You can see how this could be a problem, as you need to put together a translation that sounds good, but still includes all of the important components of the translation. In developing decoding strategies for these translation problems, researchers learned how to have diverse translations, respect constraints, avoid garden path decoding traps, and ensure good coverage of the dataset. In a bit, we'll talk about how decoding for neural machine translation has taken many of these ideas to create better outputs for neural language models, and how even neural machine translation approaches, which are much better because of attention, continuous representations inside the model, and finer-grained representations for the input and output of the model, we still use those techniques to find the best translations. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.